Welcome all. This is lecture number 13, Eigenvalues and Eigenvectors part 2 in matrices. In the previous lecture we discussed basic properties of eigenvalues, important properties, some basic examples and one example based on eigenvector where we discussed non-symmetric matrix with non-repeated eigenvalues. In this lecture we will discuss remaining part of this particular topic. So first important results on eigenvectors. The first one is the eigenvectors of any square matrix A are not unique. It we seen in the previous lecture in the last question when we can take k or minus k as a common. So by taking a different k or minus k we get the different set of eigenvectors. Second one is lambda 1, lambda 2, lambda 3 up to lambda n are distinct eigenvalues of matrix A, then corresponding eigenvectors x1, x2, x3 up to xn form a linear independent set. Eigenvectors of a symmetric matrix corresponding to different eigenvalues are orthogonal. This point is very important. That is, if there is a symmetric matrix, then its eigenvectors corresponding to different eigenvalues are orthogonal always. Two eigenvectors capital X1 and capital X2 are said to be orthogonal vectors if x1 dash x2 or x2 dash x1 is equals to 0. So moving on to the examples based on these phenomena. So example 1. Find the eigenvalues and corresponding eigenvectors for the following matrix, and the matrix is 1 2 2 0 2 1 minus 1 2 2. So this is the normal matrix, or we can say this is a non-symmetric matrix. So to solve it, first we have to find eigenvalues, and for the eigenvalues we have to find characteristic equation. So for the characteristic equation we have determinant of a minus lambda equals to 0. So with the same manner we get this particular determinant 1 minus lambda 2 2 0 2 minus lambda 1 minus 1 2 and 2 minus lambda equals to 0. Now expand this determinant uh, with respect to any row or any column, and after expanding we get a cubic equation lambda cube minus 5 lambda square plus 8 lambda minus 4 equals to 0. This is the characteristic equation in lambda. So to solve this cubic equation with the help of heat and trial method, we get lambda equals to 1 2 2. So this is the case of non-symmetric matrix with repeated eigenvalues. So let capital X1, capital X2 and capital X3 are eigenvectors corresponding to eigenvalues 1, 2 and 2 respectively. So for lambda equals to 1, from a minus 1 capital X1 is equals to 0. So directly putting lambda equals to 1 in this particular determinant and convert it into the matrix, we get 1 minus 1 equals to 0, 2 2 as it is, 0, 2 minus 1 is 1 and 1 as it is, minus 1 2 as it is, and 2 minus 1 is 1. So this is the matrix for this particular case. So find the rank of this matrix by the echelon form, and for the echelon form first element should be unit. So we can replace or we can interchange R1 and R3. So on interchanging R1 and R3 we get minus 1 2 1 0 1 1 and 0 2 2. So now these two already 0, so no need to convert it minus 1 into plus 1. We directly get this also, this second diagonal element is unit, so make this element 0. And how to make it 0? If we subtract twice of R2 from R3, then we can get these two elements are 0. So applying R3 as R3 minus 2 R2, and after applying we get minus 1 2 1 0 1 1 and 0 0 0 x1 x2 x3. So the number of non-zero rows are 2 and the number of unknowns are 3. So the rank of the matrix is 2 and the number of unknowns are 3. So the uh, case is of consistency and infinite number of solution exists, that is the non-trivial solution exists. So and the difference is 1, so we can let one scalar in this particular case. So rewriting this matrix in the form of equation, we get minus x1 plus 2x2 plus x3 equals to 0 and x2 plus x3 is equals to 0. Let this is equation number 1 and this is equation number 2. Since we cannot get the value of any variable directly from here, so we can let x3 in term of any scalar k. So let k x3 is equals to k, and putting in equation number 2 we get x2 equals to minus k, and now putting x2 and x3 in 1 we get when we put x2 equals to minus k, then this will convert into minus 2k. X3 is equals to k, this is k, so minus 2k plus k is minus k, and minus x1 minus k is equals to 0, or x1 is equals to minus k. So we get the value of x1 x2 and x3 in term of k, and k is any scalar. So capital X1 is equals to x1 x2 x3 minus k k, and now here the same situation arises. Either we can take k as a common or minus k as a common. So if we take k as a common, then this will be minus 1 1. So for lambda equals to 2, from a minus 2I, capital X2 is equals to 0. So putting lambda equals to 2, so this will be minus 1 2 2 0 0 1 and minus 1 2 0, x1 x2 x3 is equals to 0 0 0. So this is the 0. We can convert this minus 1 directly 0 with the help of R1. So applying R3 as R3 minus R1. So this will be minus 1 2 2 0 0 1 0 0 minus 2. Again we can also make it 0 with the help of R2. So applying R3 as R3 plus twice of R2, and after applying we get minus 1 2 2 0 0 1 and 0 0 0. So we cannot apply any operation further. So the rank of the matrix is 2 because the non-zero rows are first two rows, and the number of unknowns are 3. So the same case arises just like previous. That is, the system of linear equation is consistent and non-trivial solution exists. So in this case we make two equation. One is minus x1 plus 2x2 plus x3 is equals to 0, and another one is x3 is equals to 0. So from equation number 4 we get the value of x3 which is equals to 0, and on putting x3 in equation number 3 we get minus x1 plus 2x2 is equals to 0. Let it is equation number 5. Now we can let either x1 or x2 in term of any scalar. So letting x2 is equals to k. So from here x1 is also 2k. So we get the value of x2, x1 and x3 in term of k and 0. So the second eigenvector is capital X2 is equals to x1, x2, x3, or 2k, k0, or taking k as a common. So 2 1 0. Now see, there is another eigenvalue which is 2, which is same as the previous x2. So when we again find the value of we try to find again the eigenvector at lambda equals to 2 again, then the same eigenvector arises, that is 2k k0. It means uh, it depends on the k. So the same eigenvector will arises. So this is the case of uh, geometric and algebraic multiplicity. This will discuss in the next lecture. So here x2 and x3 both are the same vector. So we can write x2 is equals to x3 as 2 1 0. So the capital X1, X2 and X3 are the required eigenvector for the given matrix. Example 2. Find the eigenvalue and corresponding eigenvector for the following matrix. And the matrix is 8 minus 6 2 minus 6 7 minus 4 2 minus 4 3. If we see this matrix, first row is identically same as first column, second row is identically same to second column, third row is identically same to third column. So this is the symmetric matrix. So this is the third case. Now we will discuss or we will solve it with the same manner. So for characteristic equation, putting a determinant of a minus lambda is equals to 0. So this is 8 minus lambda minus 6 2 minus 6 7 minus lambda minus 4 2 minus 4 3 minus lambda is equals to 0. So on simplifying, on expanding this particular determinant and simplifying, we get lambda cube minus 18 lambda square plus 45 lambda equals to 0. This is a cubic equation, and this equation is known as characteristic equation. So on solving this, we can take lambda as a common from here. So the second part will be lambda square minus 18 lambda plus 45, which is a quadratic equation. So on solving it, we get lambda equals to 0 3 15. So this is the third case, symmetric matrix with non-repeated eigenvalues. So to find the eigenvector, we let capital X1, X2, X3 are the eigenvectors corresponding to eigenvalues 0, 3 and 15 respectively. So for the first eigenvector at lambda equals to 0 from a minus 0 I, capital X1 is equals to 0. So putting lambda equals to 0 here and converting this determinant into the matrix, we can get directly 8 minus 6 2 minus 6 7 minus 4 2 minus 4 3 x1 x2 x3 is equals to 0 0 0. Now we have to find rank with the help of Eigen form. So applying R2 as 4 times of R2 plus 3 R1 and R3 as 4 times of R3 minus R1. So since we have to make it unit, but in this particular case we cannot make it unit directly, only there is one option, we can divide entire row by 8 so that we can get the 1. But here the main motive is we have to find the rank, and for this we have to make these two elements 0. So for this we can directly apply this kind of operation so that these two are the zeros. So this will be 8 minus 6 2 as it is, minus 6 4 ja minus 24 plus 8 3 ja 24, so this is 0. 7 4 ja 28 and minus 6 3 ja 18, so this is 10. Minus 4 into 4 minus 16 plus 6, so minus 10, same as 4 time of R3, that is 4 2 is 8 minus 8 0, minus 16 and plus 6, so minus 10, and 3 4 is 12 minus 2, it is 10. Now R2 and R3 both are the same almost, so we if we add R3 in R2, then R3 will be 0. Or first divide R2 by 10, so we get it 0 1 minus 1 and 0 minus 10 10. Now applying R3 as R3 plus 10 time of R2, so 8 minus 6 2 0 1 minus 1 and 0 0 0. So the operations are completed, the rank of the matrix is 2 and the number of unknowns are 3. So the system of homogeneous linear equation is consistent and non-trivial solution exists. So in this case, we let the equation in form of 8x1 minus 6x2 plus 2x3 is equals to 0 and x2 minus x3 is equals to 0. These are the equation 1 and 2. So we cannot get the value of any variable directly. So for this, the difference is 1. So we can let one scalar here. So letting x3 is equals to k and putting in equation number 2, we get x2 is also equals to k. So now putting x2 and x3 in 1, we get 8x1 minus 6k plus 2k. So it will be 8x1 minus 4k is equals to 0, or x1 is equals to 1 by 2k. So capital X1 is equals to x1, x2, x3, or k by 2, k and k. So we can take 1 by 2k as a common, so that this eigenvector will convert into 1 2 2. So this is the first eigenvector. We are solving this problem in the same manner. All the problem can be solved in the same manner, but the only difference arises when the roots are repeated. So here roots are not repeated, so we can solve it in the same manner. So for the lambda equals to 3 from a minus 3i, capital X2 is equals to 0. So when we subtract, when we put lambda equals to 3, then the matrix will convert into 5 minus 6 2. minus 6, 4, minus 4 and 2, minus 4, 0. So make it unit. First, how to make it unit? Either subtract twice of R3 from R1, we can get it 1, or divide R1 by 5, or add R1 and R2 and then make negative of R1, then we can get it unit. So the first condition, R1 can be written as R1 minus twice of R3. So this will be 5 minus 4 is 1, minus 6 plus 8 to 2, and 2 remains as it is, and the remaining matrix are same. So now make these two elements 0. So we can apply R2 as R2 plus 6 time of R1 and R3 as R3 minus 2 time of R1. So after applying it, we get 1, 2, 2, 0, 16, 8 and 0, minus 8, minus 4. Now see, can we make any of R2 or R3 0 with the help of R2 and R3? Yes, we can make. So applying R3 as twice of R3 plus R2, and after applying it, we can get is 1, 2, 2, 0, 16, 8, 0, 0, 0. Now it is totally up to you whether you want to divide R2 by 8 or not. If you want to divide, then you can divide, and if you don't want to divide, then you can remain it as it is. Now the rank of the matrix is 2 and the unknowns are 3. So the same case arises, the system of homogeneous linear equation is consistent and the infinite number of solution exist. So first we dividing R2 by 8. So this will be this kind of matrices. So we can write this matrix in the form of equations as x1 plus 2x2 plus 2x3 is equals to 0 and 2x2 plus x3 is equals to 0. We cannot get any variable directly from these two equations. So the difference of the rank and the number of unknowns is 1. So we can take one scalar here. So letting x3 is equals to k, so x2 is equals to minus k by 2. Putting x2 and x3 in 3, we get x1 is equals to minus k. So we have x1, x2 and x3 from here. Since see, we can take in the each case k, or we can take k1, k2 and k3. So we can take different scalar, or we can take same scalar here. So there is no effect of it. So putting x1, x2 and x3 in capital X2, so we get minus k by 2 and k. Now either you want to take k by 2 as a common or minus k by 2 as a common, it is totally up to you. If you take minus k by 2 as a common, so this will be 2, 1, minus 2, and if you take only 1 by 2k, then this will be minus 2, minus 1 and 2. 4 lambda equals to 15 from a minus 15I, capital X3 is equals to 0. So putting lambda equals to 15, this equation arises minus 7 minus 6 2, minus 6 minus 8 minus 4 2 minus 4 minus 12 x1 x2 x3 equals to 0 0 0. So simplifying it, first we write R1 as R1 plus 4 time of R3, so that we can convert it into the unit. So this will be minus 7 plus 8 is 1, minus 6 minus 16 is minus 22, 2 and minus 48 is minus 46. Rest matrix remains as it is. Now make these two elements 0. So we can apply operation as R2 as R2 plus 6 time of R1 and R3 as R3 minus 2 time of R1. So after applying the operation, we get 1 minus 22 minus 46 as it is, minus 6 plus 6 is 0, minus 8 and this will be minus 132. So this will be minus 140, minus 4 and minus 46 into 6, that is minus 276. So this will be minus 280 and 2 minus 2 is 0, minus 4 and plus 44 to plus 40, minus 12 and this will be 80. So now we can divide R2 by minus 140 and R3 by 40. So after this dividing, we get the similar matrices. Now we can make this R3 0. So applying operation R3 as R3 minus R2. So after applying the operation, this will be 1 minus 22 minus 46, 0, 1, 2 and 0, 0, 0. So the same case arises, rank is 2, number of unknowns are 3. So the system of equation is consistent and infinite number of solution exists, or we can say Li solutions here. So converting this matrix in term of a equation, just like x1 minus 22 x2 minus 46 x3 is equals to 0 and x2 plus 2 x3 is equals to 0. So from here we cannot get any variable directly, so letting x3 is equals to k. So from here x2 is equals to minus 2k, and putting x2 and x3 in equation number 5, we get x1 is equals to 2k. So capital X3 is equals to x1 x2 x3, or 2k minus 2k and k, or taking k as a common, so 2 minus 2 1 is the eigenvector. So x1 x2 x3 are the required eigenvector for the given matrix. So this is the third case where the matrix is symmetric and the unequal roots exist, unequal eigenvalues. So moving on to the next example, find the eigenvalue and corresponding eigenvectors for the following matrix. Matrix is 2 minus 1 1 minus 1 2 minus 1 1 minus 1 2. See, each row is similar to each corresponding column, so the matrix is symmetric. So solving in the same manner, from determinant of a minus lambda is equals to 0. So this will be 2 minus lambda minus 1 1 minus 1 2 minus lambda minus 1 1 minus 1 2 minus lambda. On expanding this and simplifying, we get lambda cube minus 6 lambda square plus 9 lambda minus 4 is equals to 0. This is a cubic equation. So solve it with the help of hit and trial method and long division method, or any other method by which you can get the value of lambda. We can get the lambda equals to 4 1 1. These are the, so this is the case of symmetric matrix with repeated eigenvalues. So first we have to find eigenvector corresponding to non-repeated value, that is 4. So letting capital X1, X2, X3 are the eigenvectors corresponding to eigenvalues 4, 1 and 1 respectively. So from lambda equals to 4, a minus 4i capital X1 equals to 0. So putting lambda equals to 4, we get the matrix in the form minus 2 minus 1 1 minus 1 minus 2 minus 1 and 1 minus 1 minus 2. So solving this matrix, or we have to find the rank of the matrix by the echelon form. So first interchanging R1 and R3, and after interchanging we get 1 minus 1 minus 2 minus 1 minus 2 minus 1 minus 2 minus 1 1. So make these two elements 0 with the help of R1. So applying R2 as R2 plus R1 and R3 as R3 plus twice of R1. So minus 1 plus 1 0, minus 2 minus 1 minus 3, minus 1 minus 2 minus 3. Same as minus 2 plus 2 0, minus 1 minus 2 minus 3, 1 minus 4, that is minus 3. Now see, R2 and R3 both are similar. So we can divide R2 by minus 3, and either you want to divide R3, then you also can divide R3, or if you don't want to divide, then no problem. So after dividing R2 by minus 3, we get it 0 1 1. So now we can make R3 as 0 with the help of R2 after applying the operation R3 as R3 plus thrice of R2. So this will be 1 minus 1 minus 2 0 1 1 0 0 0. So the rank of the matrix is 2 and the number of unknowns are 3. So the system of equation is consistent and infinite number of solution exists. So converting this resultant matrix in the equation form, we get x1 minus x2 minus 2 x3 is equals to 0 and x2 plus x3 is equals to 0. So letting x3 is equals to k, so that x2 is equals to minus k, and putting x3 and x2 in 1, we get the value of x1 which is equals to k. So the capital X1 is equals to k minus k, or taking k as a common or putting k equals to 1, we get 1 minus 1 1. So this is the first eigenvector capital X1. Now for lambda equals to 1, from a minus 1i capital X2 is equals to 0. So when we put lambda equals to 1, then the matrix will be 1 minus 1 1 minus 1 1 minus 1 and 1 minus 1 1. X1 x2 x3 is equals to 0 0 0. So applying the operation R2 as R2 plus R1 and R3 as R3 minus R1. So when we apply this operation, minus 1 plus 1 0, 1 minus 1 0, minus 1 plus 1 0, and 1 minus 1 0, minus 1 minus 1 0, and 1 minus 1 0. So these two rows will be 0. So the resultant matrix will be 1 minus 1 1, 0 0 0, and 0 0 0. So the rank of matrix is 1 and the number of unknowns are 3. So the system of homogeneous linear equation is consistent and finite number of solution exists, and there is the difference is 2. So we can let 2 scalar here. So first converting the matrix in the equation form, we get the one equation, x1 minus x2 plus x3 is equals to 0. So from the one equation we cannot get the value, so we can let two variable in term of two scalar, letting x3 is equals to k1 and x2 is equals to k2, so that we get the value of x1 is k2 minus k1. So capital X2 is equals to k2 minus k1, k2 and k1. So on replacing the value of k2 and k1 as, if we put k1 equals to 1 and k2 equals to 2, then the x2 will be 1 2 1. Now it is totally up to you, either you want to put k1 any value or k2 any values. If you want to put k1 equals to 0 and k2 equals to 1, then the different eigenvector exists. If you want to put any negative value, then any other eigenvector exists. So this is totally up to you, which type of value you have to put. The eigenvector will be converted in this in according to the value of k1 and k2. So now see, uh, this is this x2 is for 1 and the matrix is symmetric and the eigen values are repeated. So in this case orthogonality property exists, because we know eigenvectors of the symmetric matrix are orthogonal. So letting x3 uh, as LMN, and the orthogonal property means x1 dash x3 is equals to 0 and x2 dash x3 is also equals to 0. So x1 dash means transpose of the x1, which is equals to 1 minus 1 1, and x3 is LMN equals to 0, and when we transpose to x2, then it will be 1 2 1 in the row matrix and the LMN. Now multiplying it, so we get two equations. One is L minus M plus N equals to 0, and the another one L plus 2M plus N equals to 0. So there are two equations in L and M and N. So on solving these two equations, see, we can, if we subtract equation number 5 from 4 or 4 from 5, we can get the value of M, because both L and N both are cancelled. So on subtracting we get M equals to 0. So this is the value of one variable M, and if we put M equals to 0 in any of the equation, we get L plus N equals to 0. So for this, letting N equals to K, so that K is L is equals to minus K. So the x3 is equals to minus K 0 K, and taking K as a common or putting K equals to 1, we get minus 1 0 1. So this is the third eigenvector. So this is the main difference here. If the matrix is symmetric and the eigenvalues are the repeated, then the repeated eigenvector can be calculated from the orthogonal property. We cannot get it directly, but see, this x3 can be get from directly from here. If we put k2 equals to 0 and k1 equals to 1, then the same eigenvector exists. So this is only for the verification, but you have to apply this orthogonal property here. So the x1 x2 and x3 which arises in this particular problem here are the required eigenvector for the given matrix. These are the three cases for to get the eigenvectors here, and the one case is already discussed in the previous lecture. Hope you enjoyed this particular lecture. uh, we will meet in the next lecture with the remaining part of this unit. That is, in the next lecture we will discuss diagonalization. Thank you.